All right, this little video here is to show how the expanded algorithm and the traditional algorithm are related. Over the last few days, students have been learning about the expanded algorithm, and the main similarity between these two is that they both show repeated subtraction happening beneath the symbols, and they show the quotient being solved to the top of the problem. Now there's a difference with this one than this one, and this expanded form is probably going to look different to most parents. So with the expanded algorithm, what I'm doing is I'm just saying I'm trying to subtract repeatedly until I use up as much of that dividend as I can. When I look at this, I might say, well, I could start with 100 times 5, and that would be 500 that I could subtract from this. That would leave me with 182. When I look at this, I say, well, if I had 20 5s, that would be 100, and I could subtract 100 and I'd be down to 82. Let me see, 5 times 10 would be 50, and then I'd have 32 left. But I know that 6 times 5 would be 30, and I would solve all the way down. Now I could write it like this. I could say that I have a remainder 2 up here, and then I could compress all of these numbers together so that I have 136, remainder 2, and that's going to be the same answer that the traditional algorithm will come out with. But it's a way of teaching students that you're keeping track of the number of 5s that are being subtracted in large groups. 500 5s, excuse me, 100 5s, 20 5s, 10 5s, and 6 5s. Here we go on this side, we'll do it the same way. The difference here is, of course, we're thinking in terms of place value, and so we're going to consider just one digit at a time, and it'll end up making the 136 on the top like we're used to as adults. 5 times 1 would make 5, and we would subtract 5, which is very similar to this step here. It happens to be. 6 times minus 5 would be 1, and we would drop down the 8. 5 goes into 18 3 times, because 4 times would be 20. 3 times 5 is 15. Here's the 32, which is interesting because we had the 32 right here. 5 times 7 is 35. 5 times 6 is 30. And we have a remainder of 2. So they produce exactly the same quotients. It's just that the traditional algorithm is the most efficient. The expanded form is going to be adding things up on top, which then have to be compressed. So it grows basically as you work, it grows longer in both directions, while the traditional algorithm grows downhill only and finishes with the answer that's uncompressed on the top. So I'll do one more example here. You might notice that I've even anticipated on this paper that I had to leave space up here and down here to do my work, and that's awkward for a student. If you know you have less room right here, is enough room up here for your answer, that your work is going to be solved below. So 8 into 9,021, well, I could say that if I had 1,000 8s, that would be 8,000, and I could take those away and I'd be left with 1,021. Then I'd say, well, if I had 100, because it's the first easy number that comes to mind, 100 8s would be 800. It's not that I couldn't get closer through some method, but I'm just trying to make it simpler. That's going to be 21, and it's going to be 221. Okay, 8 times, well, let me see, 8 times 50. If 8 times 100 is 800, then 8 times 50 would be half of that. So that'd be 400. That's too big. 8 times 20, we'll just try that. 8 times 20 here, if I were to put this on the top, 8 times 20 is 160. I can subtract that. I get 40, I get 61. 8 times 7 is 56. And when I subtract that, I get 5. So it looks like my answer here is going to be 1,127 with a remainder of 5. Let's see if I get the same thing on this side. 8 into 9, I go once. Subtract it, I get 1. I drop down my 0. I take 1, 8 from the 10. I get 2. I drop down another 2. 8 into 22 goes twice. I get 16, and that looks like it's a 6. Drop down 1. Here's the 61 that's sitting right there again. They often will do that. There'll be a moment of similarity. 7 minus 56 right here, and I get 5 as a remainder. So this would be a way of showing the students how both of these algorithms result in the same quotients, even though they arrive at them slightly differently. And ultimately, that the traditional algorithm is a little more space efficient, even though they both would be workable algorithms to solve for a problem.